Okay, let's unpack this. We've all been, well, pretty amazed by large language models, right?
Hmm.
They write, they code, they chat. I mean, sometimes it's genuinely surprising, but there's this persistent challenge lurking underneath, a bottleneck.
Mm.
How do you get them to really grasp long documents, like a whole book or a massive scientific paper, without them just, grinding to a halt or forgetting the beginning?
Precisely. That's the core issue. The main architecture of the transformer, it's brilliant for parallelism, great for training. But that core attention mechanism, it gets quadratically expensive. The longer the sequence, the costs just explode.
Quadratically, so double the length, 4 times the cost.
Exactly, for both compute and memory. Think of it like trying to hold every single word of a super long conversation in your head all at once. Eventually, you just run out of mental bandwidth, right?
Right.
So there's this hard limit, this context window.
Right.
And that's a huge bottleneck for truly long stuff.
Right.
It's actually why we've seen renewed interest in older ideas like RNNs. They scale linearly.
Oh, okay, like Mamba and models like that.
Yeah, but RNNs have their own drawbacks. Parallel processing is harder, long-range dependencies can still be tricky.
So if attention is the problem, what if you just don't pay attention? Which sounds wild, but that brings us to today's paper. It's called Don't Pay Attention, from Avey AI.
Yeah, it's a bold title.
It proposes a new architecture, Avey, that seems to break away from both attention and recurrence. Is that right?
That's the claim. It's a radical departure. So the mission for us today in this deep dive is to really get under the hood of Avey. How does it manage this trick of decoupling sequence length from context width? How can it process these, well, arbitrarily long sequences? We'll look at its components and then, crucially, see how it stacks up against the big players like Mamba and transformers. Think of this as your fast track to understanding what might be next in language modeling.
Okay, let's set the stage then. The Transformer came out in 2017, basically took over the world of LLMs. It's everywhere now. What made it so powerful in the first place? And remind us again, what's its main weakness?
Its power really came from that recurrence-free self-attention. Before that, models process things word by word sequentially. Transformers could look at the whole sequence at once, in parallel. Huge speed up for training, massive.
Right, parallelism was key.
But as we said, the Achilles heel is that self-attention scaling. N squared, computation and memory.
To quadratic costs.
Yeah. That leads directly to the fixed context window. You just can't feed it an entire book easily. It becomes computationally infeasible. And people have tried, lots of research into linearizing attention, making it more efficient.
But those haven't quite matched up.
Generally, no. They often underperform standard self-attention, sometimes quite significantly. It's been a really tough problem.
Which led folks back to looking at RNNs again, like Mamba, showing some promise there.
Yeah.
But Avey walks in and says, forget both. No attention, no recurrence.
Exactly. That's the radical step. They're basically asking, if both dominant approaches have these limitations, maybe the premise is wrong. Avey argues the real problem with transformers isn't just the cost, it's the inability to effectively model dependencies beyond that fixed window.
Ah, okay, so it's not just about cost, it's about reach.
Precisely. Their big idea, what they call a paradigm shift, is to decouple context width from sequence length. What that means is the model can process sequences of any length.
Any length?
Theoretically, yes. By identifying and contextualizing only the most relevant tokens for any given token it's looking at, regardless of where they are in the sequence.
So it's not trying to remember everything, just the important bits, even if they're pages and pages apart.
That's the core concept. It preserves the influence of distant but important information in a completely new way.
Okay, I'm intrigued. No attention, no recurrence. How does it actually do that? This decoupling sounds like magic. The paper mentions 2 main parts, a ranker and an autoregressive neural processor. Let's start with the ranker. What's its job?
The ranker is, well, absolutely fundamental to handling long sequences. Imagine you feed Avey a huge document. First, it divides the document into equal-sized chunks, splits of token embeddings. Think of them as small paragraphs or sections.
Okay, chunks of text.
Right. Now, before the model predicts the next word, the ranker steps in. Its job is to find the top K most relevant other splits from anywhere in the entire document relative to the current split it's focused on.
From anywhere, even way back at the beginning.
Anywhere. It uses something called a maxim operator. It's basically calculating similarities like cosine similarity between the embeddings in the current split and all the preceding splits.
So it's like running a quick search across the whole document. What's most related to this bit right here?
Exactly. It finds the most similar chunks, based on meaning. Then it takes the maximum similarities and sums them up to rank the splits.
And it picks the top, say, 5 or 10 most relevant ones?
Something like that, the top K.
Yeah.
But then it gets even smarter. It doesn't just select them, it normalizes and weights them.
So it emphasizes the really important ones more.
Precisely. This weighted selective split interaction mechanism means the next part, the neural processor, can focus its resources just on the most informative features from those selected splits. It highlights the useful stuff, downplays the less relevant stuff.
And how costly is this ranker? Is it also quadratic?
Theoretically, yes, the ranking step itself has an ON2D complexity, similar to transformers. N is sequence length, D is embedding dimension. But, and this is crucial, the ranker is only invoked once per full forward and backward pass during training. So while it sounds complex, the effective context the rest of the model deals with at any one time is much smaller. That's a key practical difference.
Okay, fascinating. The ranker is the smart selector, decides what information matters most no matter where it is. What about the second part, the autoregressive neural processor? What does it do with the information the ranker hands over?
Right. The neural processor is where the actual understanding, the contextualization happens. It's got 3 clever subcomponents: the enricher, the contextualizer, and the fuser.
Okay, break those down for us. Enricher first.
The enricher basically takes each token's embedding and, well, enriches it. It expands the number of learnable features using a simple one-layer network. But here's a neat trick. Partial embedding bypassing.
Bypassing, what does that mean?
It means a part of this enriched embedding, they call it the head, bypasses the next step and goes straight to the end, to the fuser. This preserves some of the raw, distinctive features of the original token. It helps stop the embeddings from becoming too similar. An issue called entropy collapse, you sometimes see in deep models, keeps things distinct.
Okay, preserves the raw signal. Then what happens to the rest, the tail?
The tail goes to the contextualizer. This is really interesting. It's designed to dynamically control information flow. It splits the tail, uses one part as a sort of gate for the other part, doing a weighted sum based on cosine similarities between embeddings within that context. The key here is that its parameterization is dynamic. It adjusts based on the input itself. It can decide to ignore certain information or focus heavily on other bits.
Dynamically. So it learns what's important on the fly.
Exactly. And because it does this dynamic weighting and comparison, it inherently figures out the relationships between tokens, which means, and this is pretty cool, it doesn't need positional encodings.
No positional encodings. That's a big difference from
A
transformers.
huge difference. It simplifies things quite a bit. The model learns position and relation implicitly through this contextualizer mechanism.
Wow. Okay, so enricher adds features, bypasses some raw info. Contextualizer dynamically processes the rest, figures out relationships. What's the fuser do?
The fuser brings it all back together. It takes the preserved head features from the enricher and the newly processed tail features from the contextualizer and integrates them. It's another simple one-layer network that combines this enriched contextualized information and contracts it back down to the token's original embedding size. It's like the final step, mixing the refined ingredients with the core flavors to get the final output for that token.
Okay, that's quite an intricate dance between those components. The ranker selects, the processor enriches, contextualizes, and fuses. It sounds impressive on paper. How does it actually perform? The paper pits Avey against some serious contenders, right? Mamba, RWKV, and Enhanced Transformer plus PEEF.
It does, and the results are, well, nuanced. On short-range NLP benchmarks, tasks like scientific reasoning, common sense inference, physical reasoning, the kind of stuff models usually do well on.
Standard tests.
Right. Avey is largely comparable to Transformer plus Avey, Mamba, and RWKV7. For the smaller and medium-sized models, Avey, Mamba, and RWKV7 actually tended to do a bit better than the Transformer plus one. However, for the large model size, Avey slightly underperformed that Enhanced Transformer Plus by about 1.9%. Mamba and RWKV7 edged it out slightly too on those tasks.
Okay. So not a clean sweep on short-range tasks, especially at larger scales. Still competitive, though.
Definitely competitive. It shows it's a viable architecture, but maybe not immediately superior for everything short-range.
What about scaling, though? You mentioned cost issues with transformers. How does Avey scale up? Does it follow those chinchilla scaling laws we hear about?
The scaling experiments are really interesting. They increased model size and training tokens proportionally, the standard way to test this. And what they found was that Avey shows the steepest decline in perplexity as compute increases.
Steepest decline. meaning it learns more efficiently with more data and compute.
Exactly. Perplexity is like how surprised the model is by the next word. Lower is better. Even if Avey starts with slightly higher perplexity at smaller scales, it gets better faster than Transformer plus Mamba or RWKV7 when you give it more resources. That indicates really strong scaling potential. It suggests Avey might benefit more from future increases in compute and data than the others.
That's a very promising sign for the future. But okay, the real test, the reason we're so interested, is long-range understanding. The paper's main claim. Tell us about the needle in a haystack test. What is that exactly?
Right, the needle in a haystack, or SNIAH benchmark, it's brutal. It's designed specifically to test if a model can find a tiny piece of information, the needle, hidden somewhere in a very long document.
And how do traditional models fare?
Poorly. Once the haystack gets longer than their trained context window, transformers, even the enhanced transformer plus Brett, basically fail.
Yeah.
Their accuracy plummets. They just can't find the needle. Mamba and RWKV7 do show some ability to generalize beyond their training length, which is good, but their performance still drops off significantly as the haystack gets really long.
Okay, so the stage is set. In Avey, how does it do finding this needle in, say, a 64,000 token haystack? It's like a novel's worth of text.
This is where Avey really shines. Remember, it was trained with a context window of only 512 tokens, tiny compared to the test length. Yet across these 64K token haystacks, Avey consistently achieves good performance.
Good? Like how good?
Astonishingly good. On one task, SNIH1, basically finding a specific passkey, Avey gets 97.8% accuracy at 64K tokens.
Wow. And the others?
Mamba gets 0%, RWKV7 gets 0.8%. They're completely lost.
0%. Compared to nearly 98%. That's incredible.
Yeah, it is. On another task, SNIAH2 exact number recall, Avey beats Mamba by over 85% and RWKV7 by over 23% at that 64K length. This holds true across different model sizes, too. It's a massive difference in long-range capability.
That's genuinely mind-blowing performance. And the paper notes something even stranger, right? That Avey's performance sometimes improves as the haystack gets longer. How is that even possible?
It seems totally counterintuitive, doesn't it? But it links directly back to the ranker. As the haystack grows, the pool of potential splits for the ranker to choose from gets bigger.
More options to find relevant information.
Exactly. A longer document might actually contain more or better relevant splits for the ranker to identify and pull into the context. So its ability to contextualize can actually improve. It really highlights how effective that selective mechanism is.
Yeah.
And the paper includes extensive relation studies tests where they turn off different components, confirming that each part, the ranker, the dynamic contextualizer, the bypassing, all significantly contribute to this long-range superpower.
Okay, let's zoom out. Bigger picture. Avey throws out attention and recurrence, takes the selective approach, and unlocks amazing long context abilities. What are the broader implications here? What could this mean for AI?
Well, the ability to truly process and understand arbitrarily long sequences without costs exploding, that's kind of a holy grail in AI. Avey's approach, focusing selectively, could be a genuine game changer. Imagine LLMs that can properly read and synthesize entire legal libraries, decades of medical research, vast historical archives, not just summaries, but the whole thing.
The potential for research, analysis, complex Q&A seems enormous.
Absolutely. It could unlock new capabilities in summarization, deep knowledge extraction, complex reasoning over massive data sets, things that are just out of reach for current models. Think about asking a question that requires connecting ideas from Chapter 1 and Chapter 50 of a huge textbook. Avey aims to make that possible.
It's an exciting prospect, but
Yeah.
what's next for Avey? It's still research, right? What are the limitations or future directions mentioned?
Definitely still research. The paper points out a few things. Right now, it's focused on text and autoregressive modeling, predicting the next word. Future work could explore using it for other things, like images or audio, or adapting it for tasks like BERT does, understanding context bidirectionally.
And what about speed? You mentioned the theoretical complexity versus practical speed.
Right. They are very upfront that while the theory is efficient in certain ways, their current implementation is slower than optimized transformers in practice. So significant engineering work is needed to speed it up for real-world deployment. That's a common step from research to production.
Makes sense. But they've open sourced it.
Yes. Crucially, they've released the code and pre-trained models. That's fantastic for the research community. It lets others build on it, experiment, and hopefully optimize it.
So, wrapping up our deep dive today, Avey, A really groundbreaking architecture suggesting maybe we don't need attention or recurrence as we know them for powerful, long-context AI. It's just amazing how fast this field moves, constantly challenging core assumptions.
It really is. Avey's selective approach, finding and using that distant but vital information so effectively, it offers a truly compelling alternative path forward. It's a potent reminder that sometimes, maybe less is more, especially if that less is chosen very, very intelligently.
So think about this. What stands out to you? Imagine a future AI assistant that could read your entire project history, every email, every document, instantly to answer a complex question. No forgetting, no context limits. How could that change the way you work or learn or even just manage information? This don't pay attention idea. It might just unlock a whole new level of understanding for AI. We'll definitely be keeping an eye on Avey and what comes next.